Thanks. So yeah, this talk is going to be about like a particular topic that I've been working since the last year, and this is work done with two students in the university, Leander Thiel and Miles Cranmer, and some people at CCA, Paco, Colin, David, and some others. And we recently published a paper about this, and there's one which we might submit in like a couple of weeks. So the topic is using machine learning to improve astrophysical scaling relations. So before, let me give an overview of what astrophysical scaling relations are. Why are they useful? So one good example is the BTFR, the baryonic Tully-Fisher relation. So if you look at galaxies, if you look at their baryonic masses and their rotation velocities, you can see that it follows a very tight relation going all the way from 10 to the 12 to 10 to the nearly 7, 10 to the 6. So this is one example of scaling relations. What are they? They are just low scatter relations between properties of complex astrophysical systems. For example, galaxies, stars, supernovae, exoplanets, or clusters of galaxies. Scaling relations are often found in observation or sometimes simulation data empirically. So people when they made plots of a few astrophysical properties of astrophysical objects, they noticed there are these tight scaling relations which they found. For example, this one, and yeah, they are often found by fitting power laws to often two-dimensional data. For example, this one. Oh. Okay, so again, let me give some famous examples of scaling relations. So there is the sorry, a part of the slide is cut, but on the y-axis is the black hole mass of a galaxy. On the x-axis is the velocity dispersion of the bulge of the galaxy. You can see that there is a tight scatter relation going over a large range of parameter space. There is also scaling relations also you can find of this type, metallicity versus stellar mass, which is not exactly a power law, but it still follows a low scatter relation. And then the one I already mentioned, the baryonic Tully-Fisher relation. So finding these, it has been interesting to find these low scatter relations. People have thought about what physical mechanisms can cause these low scatter relations. In some other cases, for example, the baryonic Tully-Fisher relation, people have tried to investigate what the nature of dark matter could be, because you have a very tight relation between the rotational velocity, which is governed by dark matter, and the baryonic mass. So, a few more examples. Scaling relations also go into producing simulations. For example, people have calibrated this low scatter relation between stellar mass and halo mass, and then this actually tells you a lot about the properties of galaxy. For example, the star formation peaks around 10 to the 12 solar masses. So then, I mean, once you find these relations, you fit them, you can then use them to make simulations. Another popular one is the number of galaxies as a function of halo mass. So people have fit, not just power law sometimes, sometimes also more complicated functions like error function for the centrals, which is shown in the pink. You can have for the satellites a power law which cuts off at low masses. So these are just some types of scaling relations people in astronomy have used. Okay, then going to some important scaling relations which are used in cosmology. So one of them I think a lot of people have heard about is the Cepheid period luminosity relation. So people have found that the absolute luminosity of the Cepheid is actually a function which is almost like a power law with the log of the period of the Cepheid. So this is actually used in then finding distances to Cepheids, and then we can infer like the late time cosmological universe from relations like these. So there is this famous tension in the Hubble constant, which I mean, a lot of people must have heard. So I mean, that was derived using like some of these scaling relations by estimating like distances to objects. One another one which is used in cosmology is the Phillips relation for supernovae. So people have found that the maximum luminosity of the supernova is actually a function of the fall in the light curve within 15 days. So that is what like delta M15 here represents. And if you kind of stack them onto each other, you can see the lower right panel where it follows a very tight relation. And so then, I mean, this is how people like estimate the absolute luminosity and then calibrate distances. So finding like these relations is very like important for like many purposes. Okay, so the one type of relation that I'll be talking about is for clusters of galaxies. So what do I mean by clusters of galaxies? These are like, I think the most massive bound objects in the universe. They have masses around 10 to the 14 to 10 to the 15 solar masses. They have around like, I've shown like one of them here. They have around like 10 to hundreds of galaxies. And if you like think of it from a virial theorem perspective, like the gravitational like potential energy of a cluster should be related to the kinematics of the cluster. For example, the velocity dispersion. So if you think like from virial theorem, you would expect that the velocity dispersion should have a power law relation with the cluster mass. And actually, this is used in cosmology for estimating masses of this cluster. And this is important because we have predictions for like for a particular cosmology, how much abundance of clusters of particular mass should be. And so if we can predict, if we can measure masses of observation clusters accurately, then we can actually predict like cosmological parameters. So this is one simple relation that is used in galaxy surveys. Yeah.
So about cluster mass here, does it include like dark matter mass, or you just talk about?
Yeah, it does include. I mean, dark matter is a very like big factor of masses. So it composes around 85% of the mass of the cluster, and that is why I mean dark matter is not directly observable. So we have to predict like this mass from some observation property.
And this part is simulation or is the observation?
This is simulation, but it actually gives an idea of how much the scatter in this relation should be. So if I predict, if I observe a velocity like a velocity dispersion for a cluster, what would be the spread in the masses that I can predict? So having a relation with low scatter is important.
This is a really naive question. So you say the bottom panel is simulation?
No, it's the top panel is my bottom panel. I think is observation from observation of the coma cluster from some survey I forgot.
So the naive question is, how do they know that this is the cluster and that it's not like larger or smaller? Is it just like distances to the?
Yeah, you can measure distances. Okay, so this is done in optical surveys, but then we have actually so we actually can also like observe clusters in CMB surveys. So this uses the thermal Sunyaev-Zeldovich effect or the inverse Compton scattering effect. For example, you have the CMB photon which comes in, and in the cluster it gets like scattered by a high energetic electron. You can actually like increase the frequency of the photon, and if you observe the CMB coming from the location of a cluster, you can see that these low energy photons have actually shifted to high energies. This people can now measure very precisely. So this is like one of the plots I've shown on the bottom. This is a reconstructed plot for how the signal in the microwave would look like for a cluster. And so comparing to previous scaling relation, you can immediately see that this has a much lower scatter. So this gives a much more accurate estimate of the cluster mass. So yeah, I've shown again a prediction from a simulation, ELSSTNG. So you can see that it follows a power law relation very nicely. And so this relation called M is proportional to y to the 3/5 is coming from the Virial theorem.
So how this give estimate on the mass?
Sorry.
So how this can be used for estimating mass?
You can measure this y parameter on the x-axis, and then you can infer the mass on the using relation like these.
Does it need any model for the electron distribution?
No, I mean, so I think the only thing that goes in this relation is the integrated electron pressure, which is directly measured from a CMB survey. So I mean, it's just a power law relation. You can also try to estimate the masses using pressure profiles, but the integrated one is, I think, what is used for estimating the masses. And again, I mean, this is the Virial theorem because Y actually gives the thermal energy, and M is proportional to the potential energy. So yeah, those two are related, and you can actually doing couple lines of algebra, you can figure out this Y to the 3/5. Yeah.
So in these two slides, what caused the scatter? Is any physical reason that caused the scatter?
Yeah. Also, this will be one of the things that I will get into. So our project was actually trying to lower scatter in this relation.
But here there's a question if there's turbulence or magnetic fields, whatever, things that are maybe missing in the simulation compared to real clusters.
Yeah, that is always the case. I mean, we have to, people have been calibrating this using multiple simulations and seeing whether these estimates of the scatter agree or not. But currently, we do get an estimate of the scatter from simulation. So we have to be careful. We need to understand why is
have
this.
any data to check with?
You can actually calibrate the amplitude of this relation using weak lensing. So you can also get an estimate of the mass using weak lensing, but you cannot do it very accurately. Yeah. And so calibrating the amplitude is done that way. And I think scatter comes from our knowledge of various simulations of clusters.
So what are the radio observation we have to constrain this PE?
So these are, sorry, can you say that again?
Like a radio observation.
Yeah, but I mean, so there have been also measurements of synchrotron emission from clusters. I guess that's what you're referring to. Right now, the limits are you have to have very precise observations and precise simulations saying that what you observe is closely related to the mass. That has not been done currently for the radio surveys. But yeah. Okay, and one thing is just keep this quantity called Y, which is the electron thermal energy in mind, because I will use this quite a lot during the talk.
But just Y is directly in the terms of the observable is directly the decrement that you see in the CMB.
Yes. Yes.
It's an observable directly.
Yes. Yeah. Okay, and then just to highlight some recent improvements in observations of CMB at small scales. So, for example, in Planck, people have targeted large to medium scales, but then in the ground-based future surveys, which are currently taking data or which are being planned, we will observe the small scales or the high L modes, and we will actually. So one thing you will notice on the plot on the right is that you have a better structure at small scales, but you also have these dots. So these dots are actually clusters observed in the CMB survey. So what is happening is that these photons of the CMB, they are getting upscattered to higher energy. So at this particular frequency, you observe that it's like a black spot. And okay, to mention, I mean, there have been these surveys like CMB S4, Simon's Observatory, SPT3G, and a lot of these surveys will target that.
Graininess, here it looks as if Planck is much higher resolution, or is it just grainy for some? The act looks very smooth compared to Planck.
Yeah.
Is it just noise?
Okay, so just to give an overview of cluster cosmology, I think these scaling relations, you can use them to estimate the masses or abundances of clusters, and then you can estimate cosmological parameters. So to give a visual idea, I've shown up this plot. So this actually is, so there are these two different like cosmologies in this figure. If you normalize the abundance of cluster at redshift 0 in two different cosmologies and you go back at high redshift, you can see that the abundances like differ a lot. So these differences in abundances can actually let you constrain cosmological parameters. Here I've shown two particular surveys. The green and the blue are the ones from clusters and the rest are from other observations. One interesting thing is, I think the first observational evidence of dark matter came by Fritz Zwicky, who was observing the Coma cluster, who noticed that the motions of galaxies in the Coma cluster are actually, much faster than what you would expect if the mass was just made up of the galaxies in the cluster. And so he predicted that there should be a lot of dark matter. In German, he predicted like dunkle Materie as like the component that we cannot see. So clusters have like an interesting history for cosmology. Okay, but so all these scaling relations that I mentioned, they were like obtained by fitting curves to two-dimensional data. Most of them were like power laws, as you saw. But then the question arises that can we find better performance, like better performing scaling relations in high dimensional spaces? So people have found like these two-dimensional scaling relations. One of the reasons for it is because it is easy to visually identify low scatter relations in 2D plots. There is this question about like going to higher dimensions, and there have been like a few examples of this in the past. One of the popular example for cluster cosmology is actually the studies which there was one study by Kravtso et al. Where you can see that again on the y-axis is the mass of the cluster. So there had been relations which were calibrated with the temperature of the gas that you can measure in observations of X-ray of clusters. So you can see that this relation has a lot of scatter. There had also been cases where the gas mass was calibrated that has like a lower scatter. But then, so this study pointed out that if you do a very simple thing, you just like multiply these two things together, the gas temperature times the gas mass, that actually has the best relation. Also not shown in this plot is it has a better like scaling to high redshifts as compared to the other two relations. So there could be like examples like these where we could just be missing things because we have looked at two-dimensional plots. Okay, one other famous example for this is, I think people here would be familiar, the fundamental plane of elliptical galaxies. So earlier people had found relations between the luminosity of the cluster and the radius, or the luminosity and the velocity dispersion. But then like people later realized that you could have like a plane which goes through like quantities like these, which has the lowest scatter. For example, like, so I've shown like the individual properties in the three plots, and then in this dash plot, yeah, you can see that the plane has the lowest scatter. So there could be these high dimensional relations which could be hiding in plain sight, because we are very good at picking up relations in 2 dimensions, but not very good when there are hypersurfaces in high dimensions. And so again, I mean, just to emphasize this, there has been this is one example of a study which tried to look for tight relations in a 4-dimensional parameter space. So this is again for black holes. Like I'd shown that the black hole mass and the velocity dispersion are tightly correlated, but what if there are other factors which also play a role? So you can see that, I mean, you can look at these different 2D plots. It gets arduous as you go to high dimensions, and with these manual techniques of looking at projections or looking at residuals of some relation. And this was also the case for our project. So now getting into the problem that we tried to address. So like from the last slide, I'd shown this mass of cluster is this power law relation y to the 3/5. But then there could be other observables which could have like even a smaller scatter with the mass, and so we can predict the masses better and estimate the cosmological parameters better. So again, this is a problem. This problem is like a problem of dimensionality. You have like different profile, like different parameters for clusters measured in different surveys, but then you don't know like which of them are important or how to combine them. So one thing you could do is this same manual data analysis, like making a lot of 2D plots and trying to see if some of these are important and how you can combine them. But I think like for problems like these, machine learning tools can be of help. Machine learning tools are generally good with nonlinear fitting, and they have also a good performance in high dimensions as compared to traditional techniques. So here I've shown just a comparison of like 3 different machine learning techniques. So you have like on one side deep neural networks, which are used a lot for image recognition or for natural language processing, but they may not be like the best tools to use in physics. On the left is like the tool that we have tried to use, which is a symbolic regression. So for symbolic regression, just to give people an idea, it is a tool which can use up to 10 parameters and can be used up to like 1,000 data points. So, this is actually fairly low dimensional as compared to deep neural networks, which can use like millions of images, each with like a million pixels or something. We have tried to use like symbolic regression in our problem. Before going into like how exactly we use this, let me give like an introduction of this technique. So just to give like symbolic regression 101, what this tool is doing is that if you give it a data file, what it will find out is it will find the values in a particular column, what equations can you write with different columns that can like provide the best fit. So the input is just the data file and it will like spit out equations like these, for example. And this problem is actually quite challenging because it's an NP-hard problem. So it scales very badly with the number of dimensions. And I think like that's why, there have been some advances in genetic programming which have actually made this possible. So, just to give an overview, so this is like one of the equations. If you want to represent it in the form that these algorithms use, this looks like a graph structure. So recently people have tried to use like genetic algorithms to speed up like search for equations like these. So you have like things like reproduction, like 2 different equations you can merge together. For example, you are merging like particular parts of the 2 structures. You can have mutations, you can have crossovers. And I think because of these things, like you can now use algorithms like these in like real life problems or data sets. There is still a long way to go, but I think the development in recent years has been promising. So we use like one of the package which was written by Miles Cranmer at Princeton called PySet.
Can I ask, so is this like some set of functions that it's trying? What is it allowed to do? Is composition allowed? Is summing of things? What is it exploring? What kind of functions?
Yeah, so you have to provide a list of what it can use. So operators like these, plus, minus, multiplication, those are like some kinds of functions that it can use. You can also specify like exponentials, error functions, power law, logarithms. And so it will like try to combine the list of functions that you choose with these variables and these arithmetic operators to then give you like.
And is it allowed to do like say you allowed sine, is it allowed to do sine of the sine of the sine of the exponential, or it's just each of is composing the functions as well?
Yes, yes. So I mean, this is where I think these reproduction kind of techniques use, like you can actually replace this x1 by some like combination of nodes here. So you're essentially like composing like different things from one structure and putting them into other and trying out many things.
So since this is a genetic algorithm approach, there's no sense of convergence, right? Like if you run the same program on the same set of data multiple different times, you can get drastically different answers that all should fit relatively well. So is there a way, pragmatically that you would go about this? So, because I've tried doing this before, and I just like run 100 instances and look for whichever output looks best.
Right.
Is there a better way to do that?
No, exactly. I mean, the problem essentially is NP hard, so you cannot like say a particular solution is like the best possible solution. So yeah, I mean, it is a bit tricky, but I think like what helps is even if it gives like a good enough fit, which you can test and try to like think about, gain intuition from, I think that's still useful. So I'll talk about like one of the things that we used it for. Okay, so yeah, again, symbolic regression 101, you have a data file. What it is doing essentially is like trying out different functions. For example, for this data in blue, tries out cosine, a linear function. So it's getting closer, tries out a sine. Then, okay, goes even further, maybe like this quadratic plus sine like works very well. But it also then like goes further and then tries out like even more complicated equations. So I mean, so the question here is like, is there a way to tell which of these equations is better? Like the more complicated equations are obviously going to fit better, but so there is also like one way where.
Are you providing some sort of, so there is some cost function or something which is like how good a fit to the data?
Right.
Is there some sort of prior as to this type of function is more complicated than this other function, so pay more price if you use exponential than if you had, or something like this?
Yes. I mean, we do it in like a naive way currently. Like, so the price of a sine is 3, price of a exponential is 2, price of an addition is 1. And so if you use more of sines, you will pay more in that sense. Yeah. So I mean, here I've shown like different equations, and complexity is what Matthias was mentioning. Like as you produce more and more complex equations by whatever metric you're using, you are going to fit better, the error is going to go down. But you don't want the most complex equation. You want the simplest equation which can predict the data to the best possible extent. And so you're looking for like somewhere like this point, and this curve is called the Pareto curve, for example. Okay, so I mean this let me get back to the problem where we try to like reduce the scatter here. So our first approach was to try to cut down the parameter space. So as I mentioned earlier, it's an NP hard problem. It scales very badly with the number of dimensions. So what we try to do is there are like much faster machine learning techniques which can let you see like what parameters are important. So we first try to use like this decision tree based algorithm called random forest, which is actually quite fast. Like it runs if you have like for data sets like the one we use, it runs in like less than a second on your computer. You don't need GPUs or anything. So I've shown like some results on the right. So in the top you have the traditional way of estimating the cluster masses. In the second panel, you can see the predictions from the random forest algorithm. So what we see is like if you add things on the top of the parameter y, for example, like concentration of gas or like stellar to gas mass or the NFW concentration, you actually do reduce and scatter. And this is explicitly what I've shown in the bottom. And so I think this is a very nice way of like quickly trying out different parameters. So if you don't know like what are the best parameters already, you can quickly like give it to the random forest and see whether the predictions improve. And what we saw was that like if we add in more parameters like say mass of gas, the axiality of the cluster or the richness of the cluster, it does not improve the performance. So it seems like these the parameters I mentioned in the bottom are the ones which provide the most information for our problem. And so what we did was we used these parameters then in the symbolic regression, and here are the results. So again, in the top panel is the traditional technique. I've shown like two of the best results we got. So I like these were quite simple. We were actually a bit surprised by like finding like relations which are this simple, but so in the middle, what it is like using is y to the 3/5 minus some times 1 minus some a constant times the concentration of the gas. So this concentration of gas I've defined as the mass of the gas in the center versus divided by the total mass. Again, you have a equation again with the NFW concentration, and you can see that both of these like work quite well.
So can I ask, so the random forest figures out which parameters are important, but without knowing the dependence. So it's just like binning. What is the random forest actually doing to figure out?
Yeah, it is actually like asking a lot of like yes/no questions. So it's like a decision tree based algorithm,
but it's somewhere by roughly it's like binning as a function of CNFW and seeing whether in each bin you get smaller scatter if you bin that way, roughly.
Right, yeah. First, like trying to like make different trees based on Y, and then make further trees based on C gas, and yeah. So iteratively trying to do that. Yeah, but the downside of random forest is that you cannot like it's almost like a black box. You have a big tree, but then it's like a tree with like 50 cells and then multiple trees. So here, I mean, you are getting equations which you can like directly see whether they work. So there are a lot of advantages. So once we got these equations, we tried to think about what could be the reasons behind this. So I mean, one of the things for the second equation to work is we think like the central regions of the clusters, they are noisier than the outskirts. So this was already known in the X-ray community, but so we can use actually, I think, this fact in this second equation, and that's why it gives us like a better prediction for the cluster mass. So essentially what we are doing in the second equation is we are downweighting the central region and upweighting the outskirts. Okay, one another thing is like the conversion of gas to stars actually reduces this Y parameter called the Compton pressure. And so that is why, I mean, this other dependence M star over M gas comes in, I think, because of that.
But who's B here?
Oh, sorry?
B, who's B?
Oh, B is just another constant. Yeah.
And why is the equation, so why is there a 2 or a 3? In some cases you allowed C gas, in other CNFW. Why is it not a combination of? Yeah,
I mean, in this case, we allowed like even the C gas, but it did not pick it. Like, I mean, it has to pick the most like concise.
The second one, it didn't have CNFW.
No, second one, because I mean, okay, so one CNFW is not directly an observable. So we try to like do one with only the observable things and one with like a full thing. Both of them are important because we don't even, I mean, we also want to understand the theoretical nature of the scatter. So I mean, even this relation is important to give you physical insights into what might be happening.
So about your random forest, so another output is that from random forest, you know which parameter is like the most informative, right? Because like what is the top decision or the first decision?
Right.
So is that a good like useful input for the following symbolic regression, or you just select some useful parameter, but you don't really do like which one is the most important one from the random forest?
I mean, we did kind of both. Like we already saw in the random forest that this Y parameter, which is the one with the power law, that is like the most important. And so we use like both. We were seeing actually like in these equations, like other than Y, the rest of the parameters seem to be like almost equal importance. And if you include like these, it almost like give no importance to these ones. So, I mean, that is one way where you can also try to only use the parameters which random forest told you are important and only use that in symbolic regression. But then it's, I mean, this is not like, I mean, I mean, people have had problems in the past actually with the importance analysis. So it's not like a foolproof thing. So you should also try to like check this using different like.
So maybe you just answered this with that last statement, but is there then no guarantee that like the importance from the random forest classification is what you would see in the symbolic regression?
No, actually, there have been like some papers in like some computer science papers which have pointed that it is not like a very good metric. I mean, it is like the first metric that you can use, but yeah, and this actually gives you a very nice way of checking whether this is really working. Can we understand? Okay, so I mean, once we got the equations, I mean, we also then try to like verify whether this is true. For the relation with the concentration of the gas, one reason could be just that the central regions were noisier that I mentioned. So we try to like remove those central regions and also saw that the scatter reduces. You can also calculate the pressure profiles and see like what part of the pressure profile is the most noisy, and that is like one on the right. You can also see that the centers are noisy. So you can do this cross checks, which if you had like things from the random forest, maybe you like do not have like a direct insight into what exactly you want to check or what will generalize. Okay, but so one caveat for the previous study was that the simulation that we use is like has one particular configuration of baryonic feedback and initial conditions, and we were trying to like see whether this can hold in a more general setting. So here we used these simulations which were done by people at CCA and also like people at the university, where they have actually run a lot of hydrodynamic simulations for different cosmology and baryonic physics parameters. For example, omega matter, sigma 8, and then some parameters related to the kinetic mode feedback of supernovae, AGN, or the momentum mode feedback of like these quantities. So here is like a movie where I've shown like differences between two codes. Like there were also like simulations with two different subgrid physics codes. So you have gas density now. Okay, let me play this again. So in TNG, for the dark matter, you can see that both of these agree that dark matter should be similar. For the gas, you can see that Simba is like a bit fuzzy as compared to TNG. And for temperature, it is like very, very different. You can see already. So Simba has like a jet mode feedback. TNG has a spherical feedback, and so I mean, you like whenever you use this simulation, I think this is like a nice caveat to keep in mind that these are not like the subgrid physics is not like the truth, and so that's what our point was, to check whether our results hold, and they seem to hold on these different feedbacks and different subgrid physics. So here I've shown in the middle panel, I've shown the results that this simple equation that we got earlier, that it does hold. You have to change like parameters a bit, but it does hold for both these cases.
So you have to change the constant is different.
Yes, and so I mean, in real life, you would calibrate like these constants using weak lensing measurements, and maybe then try to like calibrate the cluster mass. But I mean, this is also another advantage. Like we know what particular quantities to tune. If you had a result from random forest, you would not know what parameter to tune for different simulations, or when you apply this method to like real life observations. This I think is one advantage. Okay, so I mean, the second thing we did is on similar lines. So in the first part, we tried to like reduce the scatter in the high mass range, because these are clusters which are used for cosmological information extraction. But then there are also like things in the low mass which are actually affected by baryonic physics a lot more. And so this simple relation based on Virial theorem actually does fail very significantly for these low mass objects. And one of the reasons is that the gas is ejected from these low mass objects due to AGN or supernovae feedback. the potential wells of these objects are smaller, and so you can have like these modes, these different astrophysical parameters changing the electron energy measurement that you can do in surveys. So we try to like see whether we can like improve this, and so again, I mean, the goal was to find some additional parameters that we can include with the parameter of interest, that was the y, and see if we can get like better prediction at these low masses. And so we saw that actually using a simple parameter, the stellar mass to gas mass ratio actually does like quite well. You can see that in both cases, like you can find improvements. So this was actually something that we came up with intuition by like looking at some other properties, and then we try to see whether try to use this symbolic regression to see whether we can like make it better. And the result we found from the symbolic regression was that it tried to like multiply concentration of stars in the numerator, saying that, I mean, maybe we should try to use like stellar mass at a smaller radius. Maybe that would work well. And so that's what we tried, and we are getting actually like much better results in the bottom panel. You can see that this deviation is almost gone.
Who's R here? How is this chosen?
R is R200C. So this is just the critical radius at which so for every measurement like the measurement of mass, you have to define a radius to do all these things.
So it's scale, so it's an R200 or something that scales with the object.
Yes. Yeah. And so it was interesting that, I mean, this simple ratio for these two different subgrid physics, it works quite well. I mean, and the reason may be just that if you have the gas forming stars, you reduce this y parameter, but then if you include like the stellar mass to gas mass ratio, so essentially what we are doing is the total baryonic mass divided by the gas mass. So I think the total baryonic mass should remain constant rather than just the gas mass, and I think that's why.
So is this a ratio just the self-formation efficiency?
Yeah, you can, I mean, consider it like that. Yeah.
So you say you can, by adjusting the star formation efficiency, to get a better fit?
So I mean, different simulations do predict like different star formation efficiency depending on the feedback they have, and it seems like even if you vary feedback by like these large amounts, you can still have like ratios like this, which I mean, the star formation efficiency like scales, and then you can, in the end, you can get these invariances across different simulations.
So are you assuming that you can observationally determine R here?
Oh,
Use this.
I mean, no, the main problem for using this in observations is actually like measurements of gas for these small objects. So the X-ray luminosity actually drops quite significantly for these low mass objects. R is actually calibrated in CMB surveys or in X-ray surveys by looking at the pressure profile. So you have like not an exact estimate, but you have like a good enough estimate of R. So that is actually what is already done to estimate the Y. So Y is also measured within the R200. Okay, so I'll quickly go over this point. So again, coming back to like these simplistic two-dimensional relations that are used in a lot of places. So we try to like, one of the other cases where this is like quite popular to use is for the halo-based models. So for example, if you want to make like simulations which have baryon, like mock simulations with baryons, what one thing people do is like try to identify halos in dark matter simulations, and then try to have some prescription for how much like baryons there should be in these halos. This is also like one of the things that enters theoretical calculations. People also do like halo model calculations where they assume like simplistic models like these. And the reason for this is it's very easy to calibrate like relations like these. You can actually take a hydro simulation and then try to make a 2D plot and then try to fit a curve to this. So it's like the simplest thing you can do. But then if you want to like go beyond this, you again like encounter this problem of dimensionality and fitting in high dimensions. So your number of galaxies in a halo or the neutral hydrogen mass of the halo could be dependent on other things like the local environment of the halo, the concentration of the halo, or the shear. So, I mean, we thought like symbolic regression could also be useful for problems like these. And I won't go into detail. So here I've just shown like two results that we had obtained in the past. We tried to kind of extend these relations beyond the halo mass, and we saw that things like the environmental shear of the galaxies, that actually does play a role. The local environment of the galaxies, I mean, that can also like enter the equations and make your estimates better. So we did try to like first fit these relations using symbolic regression, and then try to check whether the summary statistics that we got improve. So, and we found that like you can indeed like find better measurements of the power spectrum of galaxies or the H1 power spectrum, for example, if you use like relations like these.
What is the environmental shear?
Oh, this is just that anisotropy at the location of the halo. So you can have like the halo being in an overdense environment or in a sheared environment. So, I mean, yeah, one thing is like the symbolic regression picked up shear instead of the overdensity, saying that, I mean, that may be like a better function of the number of galaxies. Okay. Yeah, okay. And then to finish this, okay, so this was like question with some, I've gotten a lot, so I just made a slide out of it. So I have, okay, I'm fitting functions or high dimensional functions to data. Like, has there ever been case where like discovery of new fitting functions like led to physics? And I think there are like two very good examples. The first one is the Planck's law of black body radiation. So for example, like in the 1900s, like people had found this classical relation where you have like the intensity going at as frequency squared. And measurements actually showed that you have to have like a dip at high frequencies. And so quantum mechanics was not known at this time, where Planck like made a fitting formula to kind of fit the results from experiments that he was getting. And then later people figured out that you have to have energy quantization, and then you can use like thermodynamics to then get an exponential factor which actually does damp your intensity at high frequencies. So in the end, I mean, fitting function in this case like came first, and then like the theories actually came later. This was like one interesting example. Another one is the Newton's law of gravitation, which actually came first from Kepler's equations, which were actually like fits to the data tables that Tycho Brahe had used. So he had determined like there has to be like functions like these. The distance cubed is proportional to the time period of the orbit squared, and also like things like these ellipse equations. And then I mean, Newton could figure out like the laws of like this 1 over r squared inverse law of gravitation. So I mean, yeah, in these two cases, I mean, there were these fitting equations which came first and then gave like theoretical insights into this phenomenon. So I have actually 10 minutes, so I can actually go. So this is like a quick part 2. So this is, okay, now going to more boring things, concerning baryonic feedback from upcoming CMB surveys. So here is like one of the pictures that I took from the decadal survey. So this is actually saying that the cosmic microwave background, you can estimate like how the early universe looked like using CMB. You can estimate the composition of the universe, or how like inflation produced structures. But then CMB is also very useful for like probing structure in the late universe, because it acts like a backlight for structure in the late universe. So this is what I think this point was emphasized in the decadal survey. And there are like many ways where you can actually probe structure formation. One of them is weak lensing. The structure can actually bend CMB light. One another way which I'd mentioned earlier, and I'll also like use it now, is these these inverse Compton scattering effect, like this TSZ effect, where CMB can like interact with gas in the clusters or groups, and then you can measure the amount of gas in groups where these baryonic feedback effects are important. So okay, then like why would these gas measurements be important? So if you look at like a lot of like baryonic simulations done these days, so like a lot of them try to fit whatever they get in simulations to observations by stellar measurements, because we have had a lot of like galaxy surveys which have probed the universe, and like these simulations, they try to like fit properties of galaxies similar to what we have seen in surveys. But then I mean, you can see that these multiple hydrodynamic simulations, they all of them like fit galaxies to a good extent, but then they vary a lot as you go to small scales. So you can see that different realizations of these simulations and yeah. Okay, and so then these different effects or like different predictions given by these simulations, they affect the accuracy to which we can estimate cosmology. So here I've shown like one of the plots from the dark energy survey. This was from a talk which Alex Ayman gave a few months ago. So you can see that I mean, in this plot, what is done is like they have color coded the scales where you had to throw away information because this was affected by baryonic feedback, and so you can see that there is a lot of like information which had to be thrown due to these effects. And then there is one study which we did with Misha and Roman, my advisor. So this was actually looking at like how much information do you lose if you marginalize over galaxy formation physics. So here I'm showing one of the plots from our paper where you have like error on the Hubble constant. If you do not marginalize over like this galaxy formation physics, or if you do marginalize, and you can see that you lose like a lot of information, especially at the small scales. And so, I mean, the thing that we were looking at is like, can you use the gas measurements which these upcoming CMB surveys are going to do to try to constrain these different like hydrodynamic simulations, so you can then try to like gain cosmological information from small scales. So here I've shown like one of the like interesting examples, one of the interesting like plots where in one of the recent papers where people saw that if you use like different simulations like the Elastis TNG or the camel simulation that I talked about, they do fit very well at small scales where we already had observations of gas. But then as you go like farther from the centers of these halos, the gas that these surveys measured was like a lot different from these different simulations. And so the hope is that, I mean, using these CMB surveys, we could maybe constrain like these baryonic simulations to then try to reduce like differences between them and try to figure out like which one is like the most realistic. And coming back to this one of the plot that I had mentioned, so like I had shown earlier that you have one of these simulations in this camel suit. It has like a big variation from the relation that you get from the Virier theorem. And so like one interesting thing is that this relation actually can be measured in the upcoming surveys, and also has been measured already by one of the data releases by the ACT survey. And these measurements will actually get a lot better. And so we were thinking whether these measurements can actually help us constrain between these different like simulation feedback parameters.
How do you measure this scatter? You need a mass now.
Yes. So that's why, I mean, you have to use a galaxy survey. They use the shear from the DES survey to measure the mass, and
Galaxy lensing together.
Yes,
So it's some sort of average.
yes, it's like a stacked over things. But then you can measure like mass in particular bins and also Y for those halos. And yeah, you can consider like this relation.
But I thought I understood you said you can constrain the scatter
Oh, no, the scatter was
for the relation. The average of the relation or the scatter?
no, here we are focusing on the average, like yeah, the scatter is like much harder. Yeah. So we are seeing like which one of these points like the would best like match what people have been seeing or people might see in future surveys. Because these plot is composed of many different simulations with different feedback subgrid physics parameters.
Oh, so it's not that this scatter is not when you look at different halos, but it also includes looking at different prescriptions.
Yes, yes.
So if you were to keep one of the simulations, it would be a much tighter relation. I see.
Yes, yeah, and I think this question is also better addressed in this plot. So we were trying to like, so these camel simulations, they have like these different feedback parameters. So we were trying to see like what particular like feedback parameters, how do they affect halos in this range. And so, I mean, you can see on the right, I've highlighted these two cases which produce the biggest effect. So if you actually increase the supernova wind speed, the relation actually goes back to the virial theorem relation. And I think this happens because you heat the gas, it cannot form stars. And so it stays close to this virial theorem relations. But otherwise, like once it forms stars, you reduce this Compton Y, or once you have a lot of like baryonic feedback, you can also then eject the gas out due to that. And so that is shown in the bottom panel where you increase the AG and jet speed. It actually like kicks the gas out of these small halos, and you can see this kind of like this rich dependence on these feedback parameters. And so we then try to like go to a next step and then try to explicitly like plot this and see like how much the future surveys can constrain this parameter space. So here I've shown these plots. In this plot, like the elasticity NG and the Simba, these were these two simulations. It is interesting that they lie like a bit different from each other. And so these small dots are actually the variations in these baryonic feedback parameters in these simulations. And they also do cover like some part of the parameter space. And the axes are just this Y measurement at high mass and Y measurement at low mass. So like in this previous plot, I mean, so I've shown this plot here. So basically we are comparing the Y measurements at a bin here and a bin here. And then we try to include like some of the forecasts that were made using CMB S4 like parameters and a galaxy survey called DESI. And you can see that it will actually like constrain a lot of these parameter space. And so it is interesting that, I mean, these upcoming surveys can actually like give a lot of insights into these maybe different like feedback prescriptions that these simulations use. Okay, and then this is related to the previous slide. We also try to then look at like other things which can help us like distinguish between these different feedback prescriptions used in these hydrodynamic simulations. And one of the things we realize is like CMB spectral distortions also do produce like these tight constraints. So I mean, just to give an overview, like the CMB is a black body, and people have like measured it like at to a very like nice precision using the previous surveys. But if you would have had surveys like Pixie, you could actually like if you measure this even better, you can actually have like much tighter constraints on these different simulations. So for example, in this plot I've shown, if you measure the mean of the Compton Y, which is essentially saying that you can measure the electron pressure like integrated over all line of sights. And if you can measure the electron temperature integrated over all line of sights using these measurements called spectral distortion measurements, you can have like a good handle on baryonic feedback. Yeah, I think, okay, let me conclude here. So the first part of the talk, I mentioned using this tool, symbolic regression, to improve astrophysical scaling relations and increase their precision. We used it for reducing the scatter in the cluster mass relations that people have used in previous surveys. And we found that using a parameter for the gas concentration actually reduces the scatter and helps you estimate cosmological parameters better. And so I'm also looking for suggestions for other scaling relations where this could be used. I think this is a general tool, and there are a lot of two-dimensional relations which are used in astrophysics, and there could be like better relations hiding in plain sight, which we just haven't tried out, and maybe these tools can help us. That is like one of the motivations. And towards the end, I discussed how upcoming CMB surveys, which will probe the ionized gas in the universe, they will help us get better constraints on the subgrid prescriptions used in these simulations.
Thank you. Any questions? Yes, Sanshi.
I have two questions. So one question is about your cluster mass estimate. So now you have a formula basically, and have you like checked some a few real cases like from observational data where there's some other mass measurement from observations like lensing? Like, do you check like how well they agree with each other?
I mean, that is one of the steps that we are thinking about. So one thing in our case, what we did was we did calculate the spherical distribution for the cluster. So these relations were based on a spherical distribution for the cluster, but we don't observe the full 3D spherical distribution in data. We observe the projection. So we were first trying to see whether these relation also works for the projected data, and then we would try to do like what you mentioned.
But in principle, you can still like do the same thing on projected or observed parameters, right? So,
Yeah.
So you mentioned that these are 2D from observations 2D. It's projected parameters. But in principle, you can do the same thing for your symbolic regression on projected. Like
I mean that. Yeah, we have to do that step. So we are thinking about that. Yeah.
And my second question is also related to this. Is that so? Here you learn from simulation data. So probably we will have very small errors on each parameters, probably. But can you do this symbolic regression directly on observational data where there can be a lot of error or uncertainty in each parameters? Like, can that work?
Yeah, it can work on noisy data. So you can specify like what the error bars on these points are, and it can include that in the equation it fits. We haven't, tried that. The simulation data is the most easy to acquire and train on, but if people can include or real life observation data on some of the relations that I showed, like the supernova or these Cepheid relations, which we don't like for these clusters, we had a Virial theorem which at least predicted this power law. For the other things, it's just people have fit one particular like power law to this data, and there could be like other relations which, if you can fit on those data sets, would be interesting.
Yeah, thanks for the talk. So I'm curious if somehow we find a certain subgrid model that that completely agrees with observations. I'm curious what conclusions the field will make about that subgrid model.
So at least like it would help us pin down cosmological measurements on small scales. So currently, like these different predictions, they affect our knowledge of cosmology at small scales, and that would be like one thing where if you have a better handle on what prescriptions are like closer to reality, it can help us with these cosmological measurements at small scales.
But do you think that that it will be assumed that if it does replicate observations, then these subgrid models are the nature of reality?
It is always like an iterative process. I don't think there will be like a particular like model which will explain. As observations get better, these models have more hoops to like jump from, and we are like continually making these these models better. Like as Nadia mentioned yesterday, I mean, for example, like previous simulations did not use Asian feedback, and now it has been established that you do need Asian feedback of some kind to replicate observation. So we will like progress along these lines. I don't know if there will be ever be convergence, but I mean, even if we like tighten our error bars, that's still important for like cases like cosmology and galaxy formation.
So a couple of questions. One, have you looked at the Magorian relation with black holes? Because there people went from the mass to the velocity dispersion of the bulge. Or maybe you can look at other parameters and if you can get an even tighter relation.
Yeah, actually, this was like one of the things that yeah, David Spergel has also like had mentioned about this. Like if there was like a good data sets, we could like try to look at these black hole relations and try to determine if there are like more parameters that could be added to make this even tighter.
And yeah, and I guess so. I guess there were the supernovae, but maybe they're very sophisticated, so maybe they've tried all of these things already with the type 1a.
I mean, I saw that they included more terms which are still linear. Like they included like a term for the metallicity, but it is still linear, and it still like takes a lot of effort to like explore a high dimensional space. And so, I mean, currently like acquiring the data is a bit hard for these simulation sets. So, but I mean, in case like you have like these data files available, one could use in principle these algorithms. I mean, they can also be used as a check. If you think like you have done the optimal analysis, then these things might give you what you already know. But sometimes, I mean, if you have missed something, these can give you some better results.
The other thing, so can you go to, you had a plot just before you looked at the y versus m, you had this plot of the correlation function that was where the data seemed to be different from all of the simulations. Yeah. So what does this mean? What's wrong with all the simulations?
So, I mean, so these are actually like scales of gas inside like virial radius of halos. We already had like measurements for these scales, and so simulations had tried to fit these scales. But then this was a test whether like can the simulation generalize outside things that they have been fit on, and it seems like from this curve it seems like no. And so this has been a lot of simulation. So this has been actually all the simulations that I talked about in the camels data set. I mean, they tried to fit, so this study tried to fit emulators to them, and but then all of them seems to have like been in this space. And so there seem, okay, so essentially it is that the gas outside virial radius seems to be hotter than all these simulations he's predicting. So yeah, maybe they can tune it and easily match it, but this is, I think, still an open question.
Gas from where?
So this is actually gas slightly away from the virial radius of these groups. So these are halos of like 10 to the 12.5 solar masses, and if you look at like gas going outside, like so, I think yeah. So this range is around the virial radius, and if you look at gas outside the virial radius, I mean there had been no measurements of these gas outside this virial radius before like surveys like the CMB survey. So yeah, this was an extrapolation from simulation and does not seem to agree. But people are, I mean, I know like many people are now working on these things. But this was a motivation to, I mean, gas can actually maybe help you constrain these things better.
Any more questions? Anyone, any question from Zoom? So let's then close there.
Thank you.